All right, so in this lesson, we're going to take a look at some extra stuff on limits here, and specifically, we're going to look at these three things. We want to be able to show if a limit exists, and we want to do this a little bit more formally than what we've been doing up until now. We want to be able to evaluate limits using what are known as the limit laws. So we'll take a look at those, and we'll introduce something called L'Hopital's rule, which is another strategy for evaluating limits that we haven't talked about yet. So showing if a limit exists. We've seen this definition before, that the limit as x tends to a of f at x is equal to L, where L is some value. This limit exists if and only if the limit as x approaches a from the right of f at x is equal to L, and the limit as x approaches a from the left of f at x is equal to L. So we called these the right-sided and the left-sided limits, and we said that these two, the limit from the left and the limit from the right, had to be the same if the limit was going to exist. So an example kind of problem would be something like this. Find the limit as x goes to 0 of f at x, if f at x is equal to the function e to the x for values of x between -4 and 0, and is equal to x e to the x for values of x that are in between 0 and +4. We can approach this by looking at the limits from the left and the right-hand side. So algebraically, we could evaluate the limit as x tends to 0 from the left of f at x. What we have to do here is choose which branch of the function we're going to be using. So if we're approaching from the left, 0 from the left, we are in this region of the curve. We are in x values that are between -4 and 0. So this limit would be the limit as x tends to 0 from the left of e to the x. And we can evaluate this limit just by direct substitution. We can sub in 0 for x, and this is going to be 1. So the limit as x tends to 0 from the left of f at x is just equal to 1. We can also take the limit as we approach from the right. If we're approaching from the right, the limit we are interested in is, well, we're interested in this branch of the curve now because we're to the right of 0, we are at x values that are between 0 and 4. So we want to evaluate this limit instead. Limit as x tends to 0 from the right of x e to the x. And we can do this by direct substitution. We can sub in 0 for x, e to the 0. This anything times 0 is just going to be 0. So that limit works out to be 0. Now, our left-sided limit and our right side, we'll get to the 0 for in a second. What we can see here is that our limit as x tends to 0 from the left of f at x is not equal to the limit as x tends to 0 from the right of f at x. Therefore, this combined limit as x tends to 0 of f at x does not exist, because our left and our right-sided limits don't agree with each other. All right, our limit laws. So we have been basically evaluating limits where we have just said limit as x tends to a of just a single thing. What the limit laws let us do is take the limit involving something, some function that is a little bit more complicated, and break it up into smaller, simpler limits. So we could take a limit as x tends to a of something that is, two terms added together, and we could break it up into two limits that are added together and evaluate these two limits separately. Same thing with subtraction. We can take a limit that is made up of limit as x tends to a of two functions that are multiplied together and break it up into two separate limits and multiply these two limits. Same thing with division. You can see same thing with a power law. Same thing with composition of functions. Why would we want to do this? Well, sometimes we're going to have situations where a combined limit is difficult to evaluate, but each of the individual simpler, smaller limits are a little bit easier to evaluate. So let's take a look at a situation here. Let's say we're not given our functions f at x and g at x. Instead, we're given graphs of f at x and g at x as shown in the graph right here. And we are asked to evaluate certain limits of combinations of f at x and g at x. So the first one here is the limit as x tends to 3 of g at x over f at x. Using the limit laws, we can think of this as the limit as x tends to 3 of g at x divided by the limit as x tends to 3 of f at x. And then we can evaluate these limits individually using the graph. If we are interested in the limit as x goes to 3 of g at x is our blue graph here. We are interested in what happens as we approach x equals 3. As we approach from the left and from the right, looks like this is going to tend to a value of 3. If we do the same thing for our red function here, f at x, as we approach 3, both the left and the right are tending towards the same value, tending towards a value of 2. So that limit is going to be 3 over 2. If you've got something like limit as x tends to 2 of f at x times g at x, again, I can break this up. This is the limit as x tends to 2 of f at x times the limit as x tends to 2 of g at x, and try to evaluate each of these independently. Limit as x tends to 2 of f at x does not exist. Because notice, as we tend to, 2 is right in here, as we approach from the left, we're tending towards a value of y equals 2. As we approach from the right, on our red function here, we're tending towards a value of 1. So this limit does not exist. The limit as x tends to 2 of g at x is just going to have a value of 2 because both sides of that blue function are tending towards 2. So if part of this doesn't exist, the entire limit is not going to exist. And we could make up something more interesting. We could do something like evaluate the limit as x tends to 0 of the composite function f at g at x. Again, we can think of this using the limit laws as the limit as x goes to 0 of f at the limit as x tends to 0 of g at x. So evaluating, starting on the inside and working our way out, if we evaluate the limit as x goes to 0 of g at x, let's see, g at x is our blue function. As x tends to 0, we are looking at a value of 0. So this would be the limit as x tends to 0 of f at 0. And then just reading off the graph, f at 0 has a value of 4 way up here. So this limit is going to be 4. Okay. So we can take a complicated limit, break it up using the limit laws into something that's a little bit easier to evaluate. Okay, finally, we're going to talk about another technique for evaluating limits that we haven't even touched on yet. And this is what is called L'Hopital's rule. So L'Hopital's rule uses derivatives to evaluate limits that are hard to evaluate or otherwise impossible to evaluate. So we haven't talked about this in Unit 910 because we haven't talked about derivatives really yet. The whole point of 910 is introducing derivatives. So the idea here is if you're coming back to this after taking a look at some of the stuff in Unit 11-12, this will make a lot more sense to you. So what L'Hopital's rule states is that if we're evaluating a limit as x tends to a of f at x over g at x, that is equivalent to the limit as x tends to a of f primed at x over g primed at x. So basically, if we have a complicated limit that involves an expression in the numerator and the denominator, or a rational function, we can take the derivative of the numerator, the derivative of the denominator, and then try to evaluate the limit again. The caveat here is this only works in cases where the limit is an indeterminate form. So when you do direct substitution, if you get something like 0 over 0 or infinity over infinity, L'Hopital's rule will work in helping you to evaluate the limit. These two are by far the most common indeterminate forms that we run into. There are other ones like 0 times infinity, 1 to the power of infinity, 0 to the power of 0, infinity to the power of 0, infinity minus infinity. But really, most often you're going to encounter 0 over 0 or infinity over infinity. Okay? So let's take a look at what this looks like when we put it into practice. Here's an example of a limit. Okay? This is something we actually know how to do. Limit as x goes to 2 of x squared plus x minus 6 over x squared minus 4. If we're following the strategies we talked about in class, our first instinct would be to do direct substitution. We would get 2 squared plus 2 minus 6 divided by 2 squared minus 4, which is 0 over 0. So we're getting one of our indeterminate forms. When we were doing this in class, we saw this as a signal that we could do something to our limit, or to the function that we're taking the limit of, that would let us evaluate that limit. And what we did when we did this in class was we factored it. We said this is actually the limit as x tends to 2 of factor the numerator and the denominator, so we've got a difference of squares down in the denominator. We can also factor the numerator to x plus 3, x minus 2, and then we canceled out these terms here. And then we went ahead and we did this by direct substitution. So we subbed in 2 for x to get 2 plus 3, and 2 for x to get 2 plus 2. And our value is 5 over 4. What happens if, instead of factoring, we apply L'Hopital's rule here? This is L'Hopital. So L'Hopital's rule would say, okay, we've got this indeterminate form, this limit that has an indeterminate form, 0 over 0. Let's take the derivative of the numerator and the derivative of the denominator. So our numerator is x squared plus x minus 6. Our derivative is 2x plus 1. Our denominator is x squared minus 4. The derivative there is 2x. And now let's try evaluating by direct substitution again. 2 times 2 plus 1, and all over 2 times 2, 5 over 4. So we get the same answer without having to do the factoring and the canceling. And once we get good at evaluating derivatives, this is going to be an easier method to use. And this can handle a lot of the cases that we're evaluating using the limit laws. So for instance, we know how to evaluate limits as x goes to infinity. So here we have the limit of that as x goes to infinity, 6x minus 13 divided by 2x plus 5. If we were to do direct substitution, subbing in infinity in the numerator and the denominator, we would get infinity over infinity, because both of these are linear functions that just go on to infinity. This is another one of our indeterminate forms. So we could do it like we did earlier in class and divide everything by the highest power of x. That would give us the limit as x goes to infinity of, our highest power of x here is just x, so 6x over x minus 13 over x, 2x over x plus 5 over x, And we know that these x's are going to cancel here and here and here and here, and that any term with an x in the denominator is going to go to 0 as we take the limit as x goes to infinity. So we would be left with just 6 over 2, or 3. Or we could try applying L'Hopital's rule. Okay, it's an indeterminate form, infinity over infinity. So this is valid. So let's take, we'll keep the limit the same, limit as x tends to infinity, and we're just going to take the derivative of the numerator, which gives us 6, the derivative of the denominator, which gives us 2. 6 over 2 is just a constant, it's 3. It doesn't involve an x at all, so nothing is changing as x tends towards infinity. So our answer is simply 3. L'Hopital's rule can even help us in complicated situations, kind of like this one here. Limit as x goes to 0 of root x plus 9 minus 3 all over x. This would be a situation where you would have to, we could do it using the strategies we had before. You would have to multiply the numerator and the denominator by the conjugate. Multiply numerator and denominator by root x plus 9 plus 3. But let's see if L'Hopital's rule applies here. So we imagine doing direct substitution, just subbing in x equals 0. We would get 0 plus 9 square root minus 3 all over 0. But the square root of 9 is just 3, so that's 3 minus 3, so 0 over 0. So we have an indeterminate form, which suggests L'Hopital's rule is going to work. Let's just go ahead. Limit as x tends to 0 of, now to do this derivative, we're going to take that root x plus 9 and write it as x plus 9 to the 1/2. And then to take our derivative, we need to use the chain rule. So we're going to bring down the 1/2, x plus 9, this will be to the negative 1/2. The derivative of minus 3 is just 0, and the derivative of x is just 1. So we have the limit as x tends to 0 of 1/2 x plus 9 to the negative 1/2. And now we can evaluate by direct substitution. We can just ignore the denominator because this is all over 1. We have 1/2. I'm going to change the negative 1/2 to 1 over the square root of 0 plus 9, which is going to be 1/2 times the square root of 9 is just going to be 3. So our limit is going to be 1 over 6. And that's the same answer you would get if you had instead solved it by multiplying by the conjugate.